Welcome to springlib.
So in this problem, we are dealing with rotations around a fixed axis and applications of this type of rotation on the given system, which is given the figure, probably given figure 15.12. And from the figure, I have written here the coordinates of all of the important points, and this is in 3D coordinate system. So x, y, z. This is x, y, and z. So first, we need to answer the question: what is the velocity at the point C? So this is a vector. You mustn't forget that this is a vector and at the point C. And we do know from from vector relationships between these tangent velocities and radius. So for example, you have radius r and you have some tangent velocity or some general velocity in that direction. We know that this, depending on the rotation, these two vector of angular rotation or of angular velocity will form a left or right triader, or it will go either like this or like this, outside or inside, depending on the direction of the velocity. So from this, we know the formula, which states that the vector of velocity is vector of angular velocity cross product or vector product with the radius as a vector. So we need to find this r and this omega in this for the given case. And this, since we are looking at the velocity at the point C, the vector of the radius vector will be basically the position vector from C with respect to the point A. So from E to C, that will be the position r vector. And from these coordinates here, we can see how can we construct that vector. So clearly, points C and point C has 0x and 0z component. Now point E has 0y and 0z component. So the resulting vector will have x component from the point A and y component from the point C and 0z component. So it will be in the plane of xy plane. And of course, this x, which comes from the point E, this here x, will be negative because this is from E to C. And therefore, we can say that R1, which we need first, is, or just R in this case, will be E. We can construct the vectors. So from the geometry of the given points, is negative 0.4 meters. Unit vector I, or for the x-axis, plus 0.15 meters unit vector j for the vertical y-axis, or it can also be a plane, horizontal plane axis, depends how you orient the coordinate system. So this is going to be the r vector. Now we need to define, we know the intensity of the angular velocity, so it's given as 9 radians per second, but we still don't know what is the vector of angular velocity. And from the described rotation, we know that this vector must be on the same line as the vector And now this is the vector from the point E to the point A. So R, this vector, and again constructed from the points, this vector will be in this form. And notice that now we're interested to find the unit vector, not this vector. So the unit vector. So we need to divide this vector with the intensity of this of the vector R, EA. So in that case, we need intensity, which will be which is 0.6 meters. So the unit vector, which can be named, for example, vector lambda, this is the unit vector for the angular velocity. So it is very important for this problem. It's going to be when we divide every component of the REA radial vector with this number here. So we divide every number here, here, and here with this number here, and we obtain this to be minus 2/3. R unit vector to J unit vector 1 K unit vector. So this is the unit vector that is very important. Why? Because now we know that rotation is going as given in the problem. It's the whole rod rotates about the line which joins the points A and B. So we need unit vector that lies on that line, and it's clockwise, which determines the direction of this vector. That is why we took exactly this direction for the unit vector. So now we can finally say omega vector is omega intensity times the lambda unit vector, which is 9 times, and then we simply add in all that is already written, and this is equal to -6 radian per second. All of the dimensions are in radian per second. All the vector components are in these dimensions. Finally, knowing this, we need to do the vector product or the cross product and obtain the velocity vector, which will be probably a 3D vector. It won't rely just on a single plane. At least I think so. We will see. So, which is equal to, now, of course, we can use different ways to perform this cross product. We can use Levi-Civita rule, which is more complicated, and in this case, it is better to use the determinant rule. So then we place in the components. This is going to be a plus. Components of the first vector in the cross product, then the second vector in the cross product, and then we start. So we basically make determinants. So this times this minus this times this. So it will be 0 minus 0.45. And in the same manner, we go for the rest of the. So minus here, and then J unit vector times, and here we have -6 times 0 which is again 0, minus, and then we have 3 times negative 0.4. Plus, and in the same manner we do for the k vector. So we look at the minor of the matrix, this form here of the determinant. Sorry. Unit vector, and when we evaluate this, we obtain minus 0.45 for the I unit vector, then minus 1.2 for the J unit vector, and plus 1.5 for the K unit vector. And therefore, this is the value of the velocity vector. So not the value, but the whole velocity vector with its components. So it's a 3D vector. This is a complex rotation, complicated rotation. So next we need to find acceleration at the same point, and we know that from the definition, acceleration is the angular acceleration from A to C. So this is about the line that goes from A to C times, and this will be also a vector, and this will also be a vector. So this plus so this is the derived formula from the textbook. So, and also knowing that we already know what this turns out to be, we can say this is angular acceleration radial vector, and then just this. So we should know that the body is rotating at the constant angular velocity, so this will be 0 as a vector, and this is not a dot product, this is a cross product, I'm sorry. So, and also here is a cross product as well. So this and this here is a cross product. So this will be 0 simply. It will be a 0 vector, so we don't really need to perform any further cross products. We'll say this is the result of this is a 0 vector, so we'll just adding a 0 vector to a non-zero vector results in the same non-zero vector, so we can basically neglect this side of the expression completely and only focus on this one. So again, we will use a determinant rule. And in the same manner as before, we obtain this is for the I, for the J unit vector, and plus 0.7. This is when we already evaluate every specific multiplication, and this ends up to be and this is the final answer for the components and the form of the acceleration vector. And also this is the end of the problem. I hope you find this helpful, and I hope to see you in another lesson.